students, welcome back to Distinction in Mathematics and welcome to the second lesson in trigonometry. We had so much fun on the previous video and I would advise that if you want to get really good marks by watching these videos, that you do watch the previous videos as well, so that you would be aligned as we move along the lessons. So before we start with today's lesson, I want us to calculate this without the use of a calculator. We mentioned on the previous video that we are going to work on this first thing before we start with the lesson for today. Now, we cannot solve this using the compound angle formula for sine because of the different angles that it has. So we will have to fix that before we move on to the next step. So we will have sine 260 degrees, cos 50 degrees, plus cos 10 degrees, sine 140 degrees. And that is the same thing I just grouped. It's starting with sine like it looks on the original compound angle formula for sine. And remember, we need to have this angle to look like this angle, and to make these angles looking identical, we can make use of 180 degrees plus 80 degrees. And when you add these two together, they will give you 260 degrees. And on this side, we'll have 90 degrees minus 80 degrees, and 80 degrees will be our identical angles. Sine 180 plus theta gives us a minus sine theta, so we will have a minus sine 80 degrees. Cos 90 minus theta gives us a positive sine theta, so we will have sine 80 degrees, and our sine 140 degrees. Now we have to make these angles to look the same, and to do that we will have to change 140 degrees to look like 50 degrees. So we will have sine 90 degrees plus 50 degrees. So sine 90 plus theta will give you a positive cos theta. So in this case, we will have a positive cos 50 degrees. Alright, so if you look closely, this has completely changed and does not look like any of our compound angle formulae. Instead, it looks like minus x plus x, which is the same as x minus x, which will give you a 0. So before we get to today's lesson, I want us to remind ourselves with these trigonometrical identities. And there we have tan theta can also be represented as sine theta all over cos theta. And sine squared theta plus cos squared theta can also be represented as 1. Double angle formulae. This is what we are going to be working on today. So I want you guys to take notice of this. If the expression sine 2a is expanded using a compound angle identity, and compound angle identities are better explained in the previous video, then a new identity is formed. So if you have sine 2a, it is the same as sine a plus a, and according to the compound angle formula for sine, you can expand this as sine a cos a plus cos a sine a. And this is the same as x plus x, which will give you 2x. So in this case, sine a cos a plus cos a sine a will give you 2 sine a cos a, because these are like terms. And that is a new identity for sine 2a. Alright, so when we look at a double angle formula for cos 2a, if the expression cos 2a is expanded using a compound angle identity, then new identities are formed. So cos 2a, which is also the same as cos a plus a, according to the compound angle formula for cos, can be expanded as cos a minus sine a sine a. Cos a times cos a will give you cos squared a minus sine a times sine a will give you sine squared a. And that is one of the new identities for cos 2a. Now you remember the identity that sine squared a plus cos squared a is equal to 1. If you make sine squared a the subject of the formula, what's on the other side of the equal sign will be 1 minus cos squared a. So sine squared a can also be written as 1 minus cos squared a. And the same goes for cos squared a. If you make it the subject of the formula, what's on the other side of the equal sign will be 1 minus sine squared a. So we can now substitute cos squared a by 1 minus sine squared a if we want to have our equation without cos, and that will give us 1 minus 2 sine squared a in this equation. So the same goes for cos. If you want to eliminate sine from the equation, you can substitute sine squared a by 1 minus cos squared a, and that, according to this equation, will lead us to 2 cos squared a minus 1, and there you have another identity for cos 2a. So these are the double angle formulae for sine 2a and cos 2a. Now that we know them, let's go to the questions. So the first one, we are asked to use a double angle formula to expand sine 50 degrees, and we already know that sine 2a will give us 2 sine a cos a. But if you look closely, the sine a cos a angles are divided by 2 from the sine 2a angle. So in this case, we have sine 50 degrees, and we will divide our 50 degrees by 2, which will give us 25 degrees, and you multiply any number that you have on this side by 2 when you get to this side. I think that is the most simplest I can explain to you, and there you will have 2 sine 25 degrees cos 25 degrees. The second one, we have to use a double angle formula for cos to expand cos 80 degrees, and we already know the identities for cos 2a. So we divide 80 degrees by 2, which will give us 40 degrees, and we will have 2 cos squared 40 degrees minus 1 because we are working on this identity. So unlike the double angle formula for sine 2a, where you multiply the number on this side by 2 when you get to this side, when it comes to cos 2a, you take the number that you have on this side and you multiply the whole identity by that number. So if you had 2 on this side, you would now have 4 cos squared 40 degrees minus 2. So since you have 1 on this side, of which there is no reason for us to make it visible because there will be no change anyway, we would have our identities as they are. So that is the first way you can expand cos 80 degrees using double angle formulae, and the second one would be cos squared 40 degrees minus sine squared 40 degrees, and the third being 1 minus 2 sine squared 40 degrees. The next one is write as sine of a single angle. There is no trick here whatsoever. They are just asking us to take it from this side to that side. So we are given 4 sine x cos x, and you remember that if you are moving from this side to that side, you multiply by 2. So when you're moving back to this side, you divide it by 2. And for this angle, you multiply by 2 when you get to this side. So you would have 2 sine 2x, and that is your final answer. Now we are going to expand 2 cos 22 degrees using double angle formula for cos, and we are going to start by dividing our angle 22 degrees, which will give us 11 degrees, and we will have cos squared 11 degrees minus sine squared 11 degrees, and we multiply the whole identity by 2. So our final answer for this identity would be 2 cos squared 11 degrees minus 2 sine squared 11 degrees. The next identity is 2 cos squared 11 degrees minus 1, and when you multiply it by 2, will give you 4 cos squared 11 degrees minus 2. And another one is 1 minus 2 sine squared 11 degrees, and if you multiply the whole identity by 2 as given, you would have 2 minus 4 sine squared 11 degrees, and that is your final answer. And now to expand 100 degrees using double angle formula for cos, we'll have cos squared 50 degrees minus sine squared 50 degrees. Another one would be 2 cos squared 50 degrees minus 1, and another would be 1 minus sine squared 50 degrees. So before we conclude with part 1 of the double angle formula lesson, we have 1 minus sine squared alpha over 2, and we have to write it as a single trigonometric function. The best way to solve this is to let alpha over 2 equal to a. So you'll have 1 minus 2 sine squared a, and this looks like one of the identities for cos 2a. So you'll have a cos 2a, and then you substitute back your alpha over 2. So you'll have 2 alpha over 2, and the 2 will cancel the other 2, and you would be left with cos alpha, and that is your final answer. Thank you for watching, students. Please place your questions on the comment section, and don't forget to subscribe and also watch part 2 of this lesson. We'll see you on the next video.